Now let's begin with this question, the area of the region. So they're talking about area, okay? So when we don't have a general formula, right? We don't have a standard structure or something. So what do I have it here? We have the area of a certain region which is enclosed by a circle, okay? Which is not common to the region bounded by the parabola and straight line. Okay, so parabola and straight line are actually creating a bounded region and we don't want that region. And then whatever the rest of the part of the circle is there, that area I wanted. Did you get the question? Let me explain that once again. They are asking for the area of the region enclosed by the circle, right? Which is not common to the region bounded by the parabola and the line. So the common region by the parabola and the line, right? There will be some common region, they don't want it. So from the area of the circle, I have to remove the common area of the parabola and the straight line. Understood? So question clearly belongs to the idea of area under the curve, right? Because we have parabola and line, right? And we have circle. So for all such question, what do? We used to study in definite integration, or rather the application of definite integration, which is the area under the curve. All right. So first of all, let's see the picture and then we'll decide how we are going to solve it. Perfect. Okay. So I am starting with the structure now. Everyone, please start with your calculation. If you want to try it, now you can try it. But let me give you some inputs. Okay. So as I said, I have to first draw the diagram. Can you see the circle x square plus y square equal to 2, the circular boundary, and the parabola y square equal to x, as well as the line y equal to x. Okay, so we have line, we have parabola, and we have the circle. Now, can you see the common portion of the bounded region with the parabola and the line, or rather the bounded region created by the parabola and the line? Can you see that? Let me show you. Okay, I have created that differential element, which I'll explain that what exactly it is coming to you or what does it mean. The shaded region which I'm talking about is basically this. Let me show you by a different color so that it is more clear to you. This is the shaded region which I'm talking about. So this is the bounded region of parabola and that line, the red color one. Can you see that? Right? Intentionally I have made that red color so that it is more visible to you, right? Not the regular one. Perfect. So this is the shaded region which I have to remove from the area of the circle. Area of the circle that you already know, pi r square, nothing big. The key takeaway is that you have to find the area of that bounded region, which is the red colored one. All right, okay, perfect. Now, in order to do that, I will be actually using that line and that parabola, right, to get that area. Perfect. And if you see, I have taken the differential element on y. See, you can choose it on x also. There is nothing wrong in that. You can definitely do that. I am taking it with respect to y-axis. So what is the situation? The situation is somewhat like this. Let's say I have a curve here. I have another curve here. Right? Or let's say if they are intersecting here and here. Right? At two places. This is what the bounded region is there. So what I can do, I can go to a certain y. I can take a differential element of dy here. Right? So dy is the thickness. So at a certain y, I actually reach to a certain dy thickness, that strip. So this is the differential strip whose thickness is dy, right? And I can quickly judge the x coordinate over here. So if I have the x coordinate, I can have the area of the differential strip. Are you getting my point? Okay. Now, so this is what I'm trying to help or like solve it with the y-axis only. Another thing that you can quickly recall, that if I have, let's say this as f of y and this as g of y, and if I want this bounded region, this one, with respect to y-axis, right? So what will we do? We actually integrate, let's say the limits or the values of y from which it is varying is a to b. Only that particular region, the shaded one which I marked here, is to be calculated. Then the formula would be integral a to b. We have this as f of y minus g of y dy. Right? See, if you observe that f of y is on the right side, or basically that particular part of the f of y is actually on the right side of g of y, right? So in terms of x values, because if you remember, the area becomes equal to, differential area becomes equal to what? X dy. So whose x coordinate is higher? Fy will have, definitely it's on the right side of gy, right? So its x values are higher. Right? Okay, and I give you the trick. The trick always works whether it is with respect to x-axis, whether it is respect to y-axis. Whatever the initial limit that you have, keep it with you. So I do have an initial limit. I will have a final limit if I want to have a bounded region. So I'll have a final limit. Okay. So these are my integral initial limit and the final limit, or the initial x or y coordinate, depending upon anything. Then which one is larger? Minus smaller. Multiplied by, it could be dx or dy depending upon the situation with with respect to which axis I'm trying to calculate it. All right, it is always larger minus smaller. So if I put it up in this way, can you see this here? This one, Fy is having actually the larger x. So this is with the larger x and this is with the smaller x. When I do the comparison of Fy and Gy, right? Because the differential area was nothing but x dy. Are you getting that idea? The same thing or the same logic is also applicable where in terms of, or rather with respect to x-axis if I want to calculate it. Let me show you. See, you're understanding it, so I'm giving you some extra key takeaways also, which you have to keep in your mind. So let's say with respect to x-axis, if I have to figure out, this is what my situation. I have some, let's say, fx here, and this is, let's say, some gx here. And again, if I want to move from A to B, and this bounded region I have to figure out. So I know that the area with respect to x-axis is nothing but what? Y dx, right? So if I go for my formula, what was the formula? The formula was nothing but we need to have an initial limit, right? Okay, and then we have a final limit. So we do have a final limit. Let me quickly write that, final limit, right? Okay, and then we have larger y minus smaller y's into dx as we are doing it with respect to x-axis. So what are the larger y's? See, clearly if fx is here, so all these y's are larger than these y's which we have here on gx, right? So clearly the graph of fx is above the gx, so it will have definitely more larger y values than gx. So if I go for my formula, the answer will become initial limit a, final limit b. Then what do I have? Larger y's. Fx is larger, gx is smaller, so we get fx minus gx into dx. That's it. You get the area. As simple as it looks. All right, understood the working, everyone? How we are going ahead with it? Keep this thing into your mind. It is always larger minus smaller, right? It doesn't matter. So I'm telling you a few situations also. It doesn't matter whether one curve is above the x-axis, one curve is below the x-axis. Doesn't matter. It's always larger minus smaller. In this case also, it is always larger minus smaller, right? You just keep this in your mind. This trick always works. It's a pretty straightforward trick. The larger minus smaller. If you're doing with respect to x-axis, you'll be taking up larger y minus smaller y. And if you're doing with respect to y-axis, then you'll be doing with larger x minus smaller x. Did you get my point? All right, everyone. Now please come back to the calculation. Okay, so I've given you enough tricks and I've given you enough hints, which I want you to remember in future, so that if in future you ever come across with such type of calculation, you have to be pretty quick. All right, so let's get back to this situation. What do I have it here? So as I said, I am doing the calculation with respect to y-axis. That's why I'm having this differential element of dy. Okay, now this is the shaded region which I was talking about. This is the differential strip, right, whose thickness is dy. All right, now if I want to have the desired area, what is my desired area or the required area is? Required area is area of the circle, and from that I will be subtracting that red colored zone, right? The area bounded by the given line and the parabola. Perfect. Okay, now if I want to have the required area of the circle is pretty simple. Why? If you talk about the equation of the circle, that is x square plus y square equal to 2. So what is the radius of the circle? I can say that the radius of the circle is nothing but root 2. So what is the area of the circle? That is pi into root 2 whole square. As simple as it sounds. So we get this nothing but as simply 2 pi. Very simple, very, very simple. Okay, so we have radius as root 2. So we got the area as pi r square. This is nothing but 2 pi. Okay, makes sense. Now, I want to have the area bounded by the given line and the parabola. Okay, intentionally, I'm calling this area as A0. All right, now I'll be calculating this A0 separately. Please listen to me carefully. This is A0. Right, look for my initial limit and the larger limit. So for that, I have to check the intersection point of those curves, which is the parabola and the line. What are the intersection point of the parabola and the line? 0, 0, origin, and 1, 1. So the parabola y square equal to 4x. Okay, let me put it up here. In fact, the parabola y square equal to x and the line y equal to x, they intersect clearly at O, that is origin, and P, which is 1, 1. So if I talk about x coordinate, they are also varying from 0 to 1. If I talk about y coordinate, they are also varying from 0 to 1. Okay, so I am intentionally choosing the y coordinate itself. Now, what is the situation here? Please listen carefully. I'm taking up only the common zone. So this is what my structure, this is what my parabola, this is what my straight line here. Right, and this is what the common zone that I have here, right? Okay, now I am erasing that shaded thing which I have just marked here. So I'm again drawing it. Just understand once again very carefully. You know what is the shaded region? I'm not be marking the shaded region now. So I have a parabola, and this parabola goes something like this, right? So the rest of the part I'm making in the dotted format. And this straight line goes like this. Then after the intersection, it is again the dotted format. Okay, so I do have a line, I do have a parabola. These intersection points are 0, 0 and 1, 1. So I'm interested only in this. Let's say if I'm observing the area with respect to y-axis, right? On this y-axis only, I want to have the area. I know that the area for the y-axis is what? Integral x dy. So I have to look for whose x is higher. The graph which is on the right side will have larger x, right? So this x equal to y is having larger x, and this one x is equal to y square will have smaller x, right? So how will I be getting this shaded region, right, or the red colored region? It's nothing but I will be going for lower limit, which is 0, upper limit, which is 1. Which one is larger? Y equal to x. But we need, see, we are asking for the area with respect to y-axis. So it becomes is equal to what? It becomes simply nothing but is equal to x dy. So the larger x coordinate is simply x, right? Okay, let me put it up in this way. So area has to be x dy, right? But it has to be larger minus smaller. So when I talk about the larger one, larger is x equal to y. So instead of x, I can put y only. Smaller one is x equal to y square. So the smaller x are y squares. And then we have dy. Are you getting the point what I'm trying to establish here? There are many things which are involved in this question. So we have integral 0 to 1 y minus y square dy. Perfect. And then I have to solve it further. Okay, that's a simple integration which you people can easily figure it out. I am putting few more values here. All right. Okay, so I'm erasing this left hand side diagram because it's already been marked here so that I can have more space for calculation. So as I said, the parabola and the line were intersecting at 0, 0 and 1, 1, right? So my desired area, shaded one, or the shaded region, that A0 become equal to integral lower limit 0, upper limit 1. Larger x are x equal to y. Smaller x are x equal to y square. So we get y minus y square dy. Let's integrate it quickly. So what do I have it here? We get this as integral 0 to 1 y minus y square. So if I integrate it, y will become y square by 2. Y square will become y cube by 3. And the limits are to be put from 0 to 1. Let's quickly put. So A0 becomes is equal to y square. If I put x equal to y equal to 1, what do I get? We get 1 by 2 minus 1 by 3. Alright. Minus 0. 1 by 2 minus 1 by 3 is nothing but what? 1 by 6. Okay. So 1 by 6 is there. So what is my required area? My required area will become is equal to 2 pi minus 1 by 6. If you take up the LCM, what do I got here? So after taking the LCM, I will be actually getting this as simply 12 pi minus 1 by 6. Right? Okay. So the desired area will become as 12 pi minus 1 by 6. Alright. This is what my final answer. And hence I'll be taking B option as the correct answer. So what was the key takeaway in this question? The key takeaway was that if you're involving two curves, right, if there is a bounded region, the bounded region is always, and the quickest and the best trick is that you look for the larger curve minus smaller curve. And then you check the initial and the final point, right? What is the initial intersection point? What is the final intersection point, right? So if I have a bounded region, I will have an initial intersection point. I'll have a final intersection point. I can get the area with respect to x-axis as well as with respect to y-axis. I have solved it here with respect to y-axis. It can easily be solved with respect to x-axis also. It will give you the same answer. Okay, so let me quickly show you the solution with the help of the x-axis also. Now, you know the intersection statistics and then the entire working. Parabola, y square equal to x, right? And straight line, which is simply y equal to x. Intersection points are origin and 1, 1. Now with respect to x-axis, so I will be looking for these differential strips, right, of dx thickness. Are you getting that idea? In fact, not the entire one will be shaded here. If I talk about this one, so if I mark it in the dotted way, this is the dx thickness which I am talking about. Got it? Okay. So now the desired area A0 will become is equal to initial limit 0, final limit 1. Sorted? Initial intersection point 0, 0. So x coordinate. See, now I'm looking the area on the x-axis. So differential element is what? Dx. So where is x is varying? X is varying from 0 to 1. Fortunately, in this question, x and y, both of them are varying in 0 to 1. So I don't have to think much about it. So initial limit 0, final limit 1. What is the larger y here? So we have y square equal to x above the graph. Like this graph is above the y equal to x line. Right? So parabola is above. So if I talk about this one, it has to be that parabola minus line. Right? But I know that the area on the x-axis is y dx. So I have to write the y values in that. Okay, so I have to write the y parabola minus y of line. Are you getting that? I'm writing the y of parabola minus y of line. Now, what is the parabola do I have? The parabola that I have is y square equal to x. So, if the parabola is y square equal to x, what does that mean? It means that my y is nothing but equal to what? Simply root x. Right? Okay, so it becomes integral 0 to 1. Y parabola is root x. And y of line is what? Simply x dx. Let's integrate that quickly. So what do I got it here? I got x to the power 3 by 2, right? Integration. After integration, it will become, see, root x is what? X raised to half. Integral will become x to the power 3 by 2 divided by 3 by 2 minus x square by 2. And limits will be from 0 to 1. Right, okay. So if the limits are from 0 to 1, when I plug in the values for a naught, what do I get it here? I get this as simply 2 by 3 minus of 1 by 2 and minus 0. Right, okay. What is 2 by 3 minus 1 by 2? It's nothing but 1 by 6. It's exactly the same value that we got with respect to y-axis. Right? So with respect to y-axis, we got the value of a naught as 1 by 6. With respect to x-axis also, we got the area as 1 by 6. Of the bounded region only, right? And then you have to subtract it from the circle. Then only the B option will become the correct answer. Understood the entire working, how we are working out with it and how the calculation is moving on. See, I'm giving you the perspective for x-axis and y-axis both because some people might get confused or why haven't you solved with respect to x-axis? Why haven't you solved with respect to y-axis? It's your choice. Advisable or the logical or the smart or the intelligent key takeaway would be if the expression of y equal to fx is simpler, use x-axis like this calculation which is in front of you as of now. Okay. And if x equal to fy is a better expression, simpler expression, then use y-axis for the calculation. All right. Trick is always larger minus smaller. If it is on with respect to x-axis, larger y minus smaller y. All right. And if it's with respect to y-axis, it has to be larger x minus smaller x. Understood? All right. Okay. So everyone, please solve some more questions based upon that if you have understood this so that you can practice it well. Right. Every question if you get in the examination of this sort in your advanced or main, doesn't matter. You must be able to solve this. All right. Guys, be ready with the complex number now. Right. So this is how you have to be very smart. Right. And you have to be comfortable with everything. Just before that, we were doing a question of PNC. Before that, we were doing a question of area under the curve. Right? So now at this moment of time, I'm doing a question of complex numbers. So in the examination hall, you have to quickly switch between the chapters, very quickly, from one chapter to other chapter. Now, as I see real part, z minus 1, now I bring all my knowledge of complex number into my brain. I try to recall everything and I read the question. Right? Read the question carefully. If real part of z minus 1 upon 2z plus iota equal to 1, where z equal to x plus iota y, then the point x comma y lies on. Options are circle whose center is, okay, so there is some center is given, or it could be a straight line whose slope is. So either it is a circle or it is a straight line, right? I have to figure it out. And then if it's a circle, what is the center and what is the diameter? And if it is the line, what is the slope? That's we have to figure out. So first of all, my aim is, but how shall I go ahead about it? So I'm giving you one particular point here. What's that point? If they have used z equal to x plus iota y, and if you have to make a judgment for the geometry, so the simplest thing that you know, how does the equation of a line looks like a linear in x and y? How does the equation of circle looks like in the standard form, that is x square and y square are having the equal coefficient and coefficient of xy equal to 0. So either of them has to appear. So better get everything in terms of x and y. That's it. That's it. That's what you have to think about. Get everything in terms of x and y. Put z equal to x plus iota y, get everything in terms of x and y so that you can better judge the curve. All right, okay, right. So the moment when I see this question, they're asking me the geometry, and I'm very much comfortable with the coordinate geometry. See, the equation of circle is there in the complex form also, right? But some of you may recall, some of you may not recall it, right? Because it's not that handy with everyone, right? Or similarly, the equation of line also in complex form, everyone might not be very comfortable with that. But as far as the equation of a circle and the equation of straight line is there, every one of you must be very, very comfortable. See, you people are doing this paper. It means that you have prepared very well for 1.5 years, right? You have put all those energy, and then you are trying to check yourself whether you are able to solve these questions or not, right? Okay, guys, great. So the aim is, as a student, I will be putting z equal to x plus iota y, so that I want to get free from all the worries to judge a complex equation of a circle or complex equation of a line. I just want to deal with the simple coordinate or the Cartesian equation of straight line or Cartesian equation of a circle, so that I can make a quick judgment. Guys, let's quickly put z equal to x plus iota y. Okay, so what was my expression, or my complex number was, I have to look for the real part of z minus 1 upon 2z plus iota, right? Okay, so if I quickly move on to it, this is the situation like, see, I have to make the judgment upon real part of z minus 1 divided by 2z plus iota. So when I put x equal to iy, I will be actually, and this real part is given to me equal to 1. This is what the central idea of the problem is, okay? But what I have to ensure here is that z is properly placed as x plus y and all this. So first of all, I'll decide about the complex number, right? Forget about the real part. I'll check out the real part. I'll remove all the real part terms together, and then I'll make it equal to 1. But first of all, let's put z equal to x plus iota y. So this is how this complex number z minus 1 upon 2z plus iota looks like this. Understood? Okay, perfect. Now, if this is there, then how shall we handle it? The easiest way to handle it, that you write the, see, if I have a division of two complex number, right? Now, if I'm a student, I will be thinking, okay, what was the division of complex number? How do we deal with the division of complex number? The division of complex number, if I have z1 upon z2, it's simply the thing that I multiplied by the conjugate of the denominator. And why do I do so? Because by doing that, numerator is z1 into z2 bar, but denominator becomes what? z2 into z2 bar, that is mod z2 square, which is a purely real number. Advantage, I get in the denominator as a purely real number. Lovely. So this is the idea behind it. If I want to deal with the division of complex number, my aim is to make the denominator as a purely real number. And if any complex number is multiplied by its conjugate, it gives me the square of that modulus of that complex number. Modulus of any complex number is always a real quantity. So its square also has to be real quantity. So this way, my denominator becomes a purely real thing. Understood? So what is my aim here? I will be actually multiplying by the conjugate of the complex number, which is written on the left hand side. So let's collect the terms with iota and others quickly. So I got this as x minus 1 plus iota y, numerator. Denominator, if I collect it, we get this as 2x plus iota times of 2y plus 1. What's my next step? Multiply by the conjugate of the denominator in the numerator and denominator both. Okay. So that I am making the denominator as a purely real number. So multiply by the conjugate of the denominator. I have this as 2x minus iota times 2y plus 1. Similarly, I multiply by this 2x minus iota times 2y plus 1. Now, denominator z into z bar. Okay. Now, just be careful with one more thing also. As I am looking for the real part of this complex number, right? Z minus 1 upon 2z plus iota. So if I'm looking only for the real part of that complex number, in the numerator, see, I know the denominator has to be a purely real number. So that is nothing but the denominator is p plus q into p minus q format, which is p square minus q square. So what do I got it here? We got this as 2x whole square, which is 4x square minus. So we get minus of iota square, but minus of iota square. So iota square is minus 1. So minus of minus 1 will make it what? Plus 1. Right? So I'm writing it as intentionally minus iota square, as p plus q into p minus q will give me p square minus q square. Fortunately, this minus iota square will become eventually as plus 1. So I'm still writing it. So the second term will become 2y plus 1 the whole square. Now in the numerator, I will be only dealing with the real part. So I'm interested only in the real part of the numerator. Why? Because I have to make judgment only for the real part. So real part of numerator. So real part of numerator will come only when I'm multiplying this x minus 1 into 2x. So we get 2x into x minus 1, as well as when this both the iota terms are multiplied, which is minus of iota squared times of y into 2y plus 1. All right. So this is a real part of the numerator. Divide by, see, that's a real quantity which will go with the real part as well as imaginary part. But my real part will look somewhat like this. So real part of the numerator, denominator is only real part. That will eventually give me the real part of that complex number. Now, so what do I have the real part of the complex number? It is 2x into x minus 1 plus y into 2y plus 1. Divide by 4x square. And as I said, iota square is nothing but minus 1. So minus 1 minus 1 will make it plus 1. So we get this as plus of 2y plus 1 the whole square. And this real part has been made equal to 1. Okay. So I'm removing this bracket so that you should not get like blurred picture of this. Everyone sorted with this. Now, I want every one of you to move your pen much faster than me. Please solve everything. Get me one simplified equation in x and y. And you have to be faster than me. Guys, please start solving it very quickly. All right, so what do I have it here? Let's multiply the numerator and I'll take everything on the right side. So 2x into x minus 1 will give me 2x square minus 2x. Y into 2y plus 1 will give me 2y square plus y is equal to 4x square plus 2y plus 1 the whole square. Okay, let's open it up and simplify quickly. So what do I have it here? We get this as 2x square minus 2x plus 2y square plus y is equal to 4x square. When I open up that 2y plus 1 the whole square, what do I got? We got 4y square plus 4y plus 1. Okay, sorted. So this one is also there. Now let's bring everything on one side. Okay, so I'll take the entire LHS on the right side. So what do I have? 4x square minus 2x square will make it what? I get this as simply 2x square. Then 4y square minus 2y square will give me what? Simply 2y squared. So 2x square plus 2y square. Now, on the right side, we don't have any terms of x. So minus 2x will come on the right side. It will become plus 2x. Similarly, plus y will go on the right side. It will become 4y minus y. That is plus of 3y. And that plus 1 was already there. We got this. Can you figure out the equation? What equation is this? Which curve is this? It's nothing but a circle. Guys, the coefficient of x square and y square are same, 2. And what do I have it here? I simply have the coefficient of xy as 0. Equation belongs to a circle. So my geometry is sure that it is a circle. Now, if it was a circle, I have to comment on its center as well as diameter. Remember the options? Okay. So I'll be actually now doing it in this way, that I will be first writing it in the standard form. So in standard form, I'll be dividing by 2. So I'll get this as x square plus y square plus x plus 3 by 2y plus 1 by 2 equal to 0. Now when I compare it with the standard equation of the circle, which was x square plus y square plus 2gx plus 2fy plus c equal to 0, I can figure out the value of g, f and c from here. So when I figure out the value of g, f and c, I can say that g becomes equal to half. I can say that f becomes is equal to 3 by 4. And I can say that c becomes equal to 1 by 2. This is the value for g, f and c here. Perfect. With this value, I will be commenting on the radius and the center of that particular circle is. Okay. So what is my center? Center will become nothing but equal to as minus g, comma minus f. That is minus 1 by 2, comma minus 3 by 4. Okay. Sorted. Now I have to comment on the radius. Then only I'll be able to go to the diameter. So let's say if I have to go for the diameter, I'll directly write diameter. So diameter is nothing but 2 times of root over g square plus f square minus c. Okay, so if I have this as under root of g square plus f square minus c, let's plug in the value. So we get 2 root over what is g square? 1 by 4. What is f square? 9 by 16 plus, minus 1 by 2. All right, and if you simplify it further, after taking the LCM and all this, what will I be getting? See, if you take up the LCM as 16 or something, so dia will become is equal to nothing but simply as 2 times of under root of, we get this as 16. So we get 4 plus 9 minus 8. So we get 13 minus 8 by 16. That is under root of 5 by 16. So we get this as nothing but 2 into root 5 by 4, which implies that nothing but root 5 by 2. What is my diameter? Root 5 by 2. So I got two things. Center as minus 1 by 2, comma minus 3 by 4, and diameter as root 5 by 2. All right, center as minus 1 by 2 comma minus 3 by 4 and diameter as root 5 by 2. All right, so my center was minus 1 by 2 comma minus 3 by 4 and my diameter was nothing but equal to root 5 by 2. So out of these four options, only C option is the correct answer and hence I'll be ticking it. All right, understood the entire working, how we are dealing with it. See, the solution was, the moment as a student, if I'm looking at the question, I have Z and they are asking me the locus and they are asking me the equation of the curve, whether it is a circle, whether it is a straight line. I am very comfortable in coordinate geometry with circle and straight line, right? So I will prefer to have this converted in terms of X and Y. That is the reason why I intentionally put Z equal to X plus iota Y. Now I'm giving you a trick, an insight in this question. Now onwards, if you come across a question where they are talking about a certain geometry, they are asking about the equation of that curve, or they are talking about the center, a radius, or let's say if it turn out to be an ellipse, then they might ask you about the focal directrix and all this, the equation of them, or if it's a straight line, the slope and all this. Basically, in nutshell, if they're asking for all the geometries which are related to the coordinate geometry, which you know, straight line, circle, parabola, ellipse and hyperbola, please strictly convert everything in terms of Z equal to X plus iota Y. The moment you talk about equation, the moment you talk about standard geometries, please put Z equal to X plus iota Y. You'll never ever have any slight confusion. The key takeaway and then the most crucial point will be here, which will set you apart, is you have to be very quick in your calculation. See, the moment when you put Z equal to X plus iota Y, it's not a big deal. It's a very simple thing. Now the difference makes in your speed. So you have to be quick, you have to be accurate. All right? Lovely. Sure? Okay. Now this one is a very interesting question. See, even it's a mains paper, some question even in mains paper are also a very, very good standard. This is one of them. This is really a nice question. And you can expect this to be as the one of the easy question of advanced if you put it up in that way. So it's this kind of question actually serve you the purpose for mains as well as for advanced both. All right, so let me quickly read this question and what are the first insights which come to my mind as a student. So the question says that if f of a plus b plus 1 minus x is equal to fx for all x, where a and b are fixed positive real numbers, then 1 upon a plus b integral a to b x f of x plus f of x plus 1 dx is equal to. Can you see my four options are with the integral limits are from a minus 1 to b minus 1 or a plus 1 to b plus 1. And that too also my expression for fx is either fx or f of x plus 1. Okay, so I have to keep this thing in my mind. Now, whenever we come across with such questions, see clearly it's a question of definite integration. And if you have the limits as a to b, and if you see that the first relation also involves something like a plus b plus 1 minus x is equal to fx, which implies that we are dealing with a plus b minus x also, then the first thing which should come to your mind with this property that, or rather this particular property has to be applied here, that integral a to b fx dx is always is equal to integral a to b f of a plus b minus x dx. This is the first impression, right? Being a student, this is the first thing which will strike to my mind. Now I know that this has to be arranged. So the data has to be arranged very wisely and we have to think in that way. So what are the two things that we are dealing with here? We have the relation for fx and they're talking about f of x plus 1 as well, which implies that I need to create the relation for f of x plus 1 as well. So these are the two insights. First one, this identity, this has to apply here, this property has to be applied here. Second thing, I'm dealing with fx as well as f of x plus 1. So I have to see the modification when I replace x by x plus 1 in the original statement or the first relation given. All right, then only we can actually think about the problem furthermore, right? And then only some more other steps will be entangled, like based upon whatever that we are calculating it further. Understood? Options clear in your mind? We have to bring in either fx or f of x plus 1. Limits have to be either a minus 1 to b minus 1 or a plus 1 to b plus 1. Perfect. Let's move on to the problem quickly. Now, this was the first statement that we had, that f of a plus b plus 1 minus x is equal to fx, right? This was the first thing. I know that I have to deal with f of x plus 1 also. So the first thing which came to my mind, other than the property, is that I need to replace x by x plus 1 so that I can establish a relation for that as well. Okay, let me quickly do that. So when I replace x by x plus 1, my relation becomes a plus b plus 1 and x is replaced by x plus 1, so minus x minus 1 is equal to f of x plus 1. What does that mean? If I simplify it further, so this 1 and 1 got cancelled. The second relation looks like f of a plus b minus x is equal to f of x plus 1. I will be calling it up as, let's say, equation number 2. Pretty good statement, right? I have to establish a relation for fx as well as f of x plus 1. My answers are even in the option in the format of fx and f of x plus 1. So I have to consider the possibilities for both of them, right? And I have to be very flexible. Perfect. And that property that we already have to apply, this also we have to keep in our mind. Perfect. Now, what was my integral expression? My integral expression was 1 upon a plus b, integral a to b, x f of x plus f of x plus 1. Now, when you have been practicing these questions, right, many questions you would have seen that this x would have been outside. Then how do? We actually move ahead with the once again the same property. That is, if I have integral a to b fx dx, that is always equal to integral a to b, then I have f of a plus b minus x dx. So this thing you have to keep intact in your mind, right? Whenever we have an x outside and other in the inside a bracket, we have some other expression. It could be algebraic, it could be trigonometric, anything. Then this is the first one of the hints which come to your mind, right? These are the few things which strike to your mind. So I'll think, okay, now I know that this property has to be applied here. So I'll try to utilize this relation in order to eliminate this x. If I'm able to get rid of this x, then I'm done. Because even if you see in my question or the answers, the options are purely in terms of integral of f of x plus 1 or fx. There is no x involved here. So x has to be eliminated and I have to do it very wisely. Okay, so I know that in this integral, I need to apply that property. So let's quickly apply that property, right? So I'm replacing x by a plus b minus x. Perfect. So my integral I got converted as 1 upon a plus b, integral of a to b. Here outside x becomes a plus b minus x. And within the bracket, we have f of a plus b minus x, the first one, plus the second one, f of x as a plus b minus x plus 1 dx. Now, please use the relation number 1 and relation number 2 to modify this relation, what we have just created here. What modification we can do? See, I know that this f of a plus b minus x is nothing but what? It's simply f of x plus 1. Similarly, f of a plus b minus x plus 1 is nothing but fx. Wow, this is the inside that we have. Yeah, this is exactly that we have. So I can also write this I is equal to 1 upon a plus b, integral of a to b. Okay, let me write it here. So this same thing can be written as integral of, okay, so 1 upon a plus b outside first of all. So 1 upon a plus b, integral a to b. We have a plus b minus x outside. And then within the bracket, the first one becomes nothing but f of x plus 1 plus fx dx. Perfect. So this is what we have. Okay, I will be calling it this one as fourth one. All right, now please look for the third one and the fourth one carefully. I would like to add this third one and the fourth one. All right, I'll in fact write it here so that we can have more clarity about it. So my fourth statement looks like that the same I is nothing but 1 upon a plus b, integral a to b. Outside we have a plus b minus x. The first one can be replaced as nothing but f of x plus 1. And the second one as nothing but f of x dx. So let's quickly add third and fourth. So when you add this, I'm calling this one as fourth. So let's quickly add third and fourth. So when I add third and fourth, can you see that the inside the bracket we have fx plus f of x plus 1 in both of them, right? Only that x and a plus b minus x, that is where they differ. Okay, so let's quickly add them. The moment when I add both of them, what will I be getting? I'll be getting 2i is equal to 1 upon a plus b will be common in them, right? In both of them it is common. It will look, and I know that f of a plus b minus x is also common in that one. So 1 upon a plus b, integral a to b, we have fx plus f of x plus 1 into, we will be having x plus a plus b minus x dx. Advantage, this x and x got cancelled, but I'm left with a plus b. Now this a plus b is a constant which can easily be dissolved with this one. What I got nothing but 2i is equal to integral a to b f of x plus f of x plus 1 dx. Simply. Sorted? Okay. So this is the modification that I have introduced from my side. Now I'll be splitting this. I know that I have to either bring f of x plus 1 or I have to bring f of x. So what I do, I split it first, right? I'm distributing the integral limits. So the moment when I distribute the integral limits, I'm keeping f of x plus 1 and f of x separately as an integral. Perfect. Then I'll try to modify the first one. Let's see what it turned out to be. See, this is the stage where I have to do some modification, right? So I'll try to begin the modification with the first one, f of x plus 1, and then we'll see how it actually figures out. Okay, I know that the answer has to be either in the terms of fx or f of x plus 1. So any one of them can be modified, right? For sure. Let's try with the f of x plus 1 thing. Okay. Then once again, I can apply the same property which we have studied, right? And which we have just quickly recalled. So I replace x by a plus b minus x. We get 2i is equal to integral a to b. We get this as a plus b minus x plus 1 dx. Second one, I'm not at all disturbing because I know that either we have to bring everything in terms of fx or we have to bring everything in terms of f of x plus 1. So I'm modifying f of x plus 1 with the same property. But from the results, we know that what is f of a plus b minus x plus 1 is, we know that this was the first statement which was given to me. A plus b minus x plus 1 is nothing but equal to what? Exactly, it is equal to fx. So I can write that 2i is equal to, the first one is integral a to b fx dx. Second one is again integral a to b fx dx, which eventually qualify them to be as nothing but 2 times of integral a to b fx dx only. So if I have 2i is equal to 2 times of integral a to b fx dx, I can also say that I is equal to integral a to b fx dx. Perfect, sorted. So we have brought everything in terms of fx. Lovely. So since there was no option of this format, so I cannot stop here. I have to solve it further, right? See, I'm a student. I can see my options. I quickly move on to the option that I saw. Oh, no option is of that format because in all the option, the integral limits are either from a minus 1 to b minus 1 or a plus 1 to b plus 1. So some modification has to be done. And the second observation that I know that either x we could have in the answer as fx or f of x plus 1. So in terms of fx, the answer has to be this, which is not there. So the only option I'm left with that I have to bring this answer in terms of f of x plus 1, which compels me to do this step. That you convert the variable. Let's assume x is equal to t plus 1, right? And the moment when I have x equal to t plus 1, then dx becomes equal to simply dt. As simple as it sounds. And the limit will also change. What are the limits? They say that if x equal to a, then it implies that t plus 1 equal to a, which implies that t is equal to a minus 1. And in the same fashion, if I have x equal to b, which implies that t plus 1 equal to b, which implies that t becomes equal to b minus 1. Lovely. So we are reaching to that result, some quite similar to that one. What do I have it here? My integral now I will be converted as lower limit will become a minus 1, upper limit will become b minus 1. And instead of x, I'll be putting t plus 1 and then we'll have dt. Wow, but my option was in terms of x. You know this property, right? You know that indefinite integration is always independent of the variable involved. Definite integration is always independent of the variable involved. Indefinite is always dependent upon the variable involved. So in definite integration, we have initial and final limit. So whatever the inside variable I'm choosing, it doesn't matter, right? Because eventually the values of t has to be moved from or will be varying from a minus 1 to b minus 1. So I can use the same result to bring it everything in terms of x. Hence, if I convert everything in terms of x, my answer will look I equal to integral of a minus 1 to b minus 1 f of x plus 1 dx. Instead of t, I'm just using the x. So change of variable is allowed in definite integration, right? Perfect. So there were many insights here. And can you understand the question how logically we have to connect it? As a student, I would have first recall the property. Okay, I know that that property I have to apply it. Second thing, my answer has to be either in fx or f of x plus 1. So I know that the outside x which was there in the question in the integral, I have to remove that. So again, I applied that property. Fortunately, when I added them with the modifications, so we have reached to that result which is free from x outside the f of x and f of x plus 1. So once we reach to this result, like the first line of this page, then we have modified it further. So I change only any one of them, any one I can change. So I've changed the first one. The moment when I change the first one, I eventually reach to this result that I is equal to integral a to b fx dx only. And then I know that my answer cannot be with the limits of a to b. My answer is either in terms of a minus 1 to b minus 1 or a plus 1 to b plus 1. And I know that instead of fx, I have to bring x plus 1. So intentionally, I'm choosing x equal to t plus 1. This is the most crucial step and very logical one. I have to get f of x plus 1. What will I do? I'll just replace x equal to t plus 1, right? So that I can create the variable f of x plus 1. Sure? Okay, and then we finally reach to this result. And based upon this, C option becomes my correct answer. There were many insights which are given in this question. Keep up all the logical hints, right? See, every time you read a question, The idea is that you have to look for the insights in the problem. How it is actually, I will be connecting it. What information that is given in the question, what results or formulas or identity which I know beforehand, what application that I have learned before while reading those properties, those are to be kept intact. And that is why we say revise as much as you can. As many number of times you will be doing the revision, you will be making yourself stronger. By revision, I don't mean that you'll be just reading the stuff again and again, right? You have to literally move your pen every time you have to reach to the answer by following these steps, right? If some people see in mathematics, if you're trying to do the revision by just reading it, this is not going to work out, guys. This is not at all going to work out, right? Please solve the question, reach to the answer correctly, mark it, generate the confidence that will surely reflect in the examination hall. All right?